I'm Rayesh Uppal, founder of IDST. We bring you sharp insights and foresight on emerging tech, defense, and security. Let's dive in.
Imagine boarding a plane that glides through the skies without a drop of jet fuel, its engines humming quietly on pure electric power. It sounds like the future, but for aviation, that future is closer than many think. With the industry under pressure to cut emissions, responsible for around 2.5% of global coal today, electric propulsion is becoming the next great leap. But here's the catch. Making electric aircraft work all comes down to one thing: the batteries. Unlike cars or trains, airplanes live and die by weight. Add more mass, and energy demands skyrocket. A car's energy use might rise just 15% with added weight, but for a plane, it's a 1-to-1 trade-off. A 35% increase in mass means 35% more energy needed just to stay airborne. That's why batteries, despite all their promise, are aviation's biggest hurdle. They're heavy, and every kilogram counts in the sky. So what does this mean in practice? Smaller regional aircraft, flying maybe 500 nautical miles with 30 to 70 passengers, are the easiest candidates for electrification. These short-range aircraft already dominate flight numbers, and their battery needs are within reach. But the big problem is the wide-body jets. They carry hundreds of people over thousands of miles, and they're the real carbon culprits. To electrify them requires battery breakthroughs that go far beyond today's limits. For example, a 30-seat commuter plane flying under 800 kilometers needs batteries delivering between 750 and 2000 watt-hours per kilogram. Right now, the best lithium-ion packs manage around 250. That's why some researchers believe fully electric regional planes could be possible by mid-century, if energy density keeps doubling every 20 years. But for larger aircraft, hybrid systems may be the only realistic option in the near term. Energy density is where the race is being fought. Jet fuel packs 70 to 80 times more energy per kilogram than today's batteries. Companies like magniX, Wright Electric, and Electrove are pushing hard to close the gap. magniX's Samsung battery now reaches 300 watt-hours per kilogram. Wright Electric is targeting 400. Electrove's designs are hovering around 350, and solid-state or lithium-sulfur chemistries could push beyond 500, with the holy grail goal of 1000 watt-hours per kilogram, enough to power larger electric jets. But energy density isn't the only challenge. Safety is equally critical. Lithium-ion cells are notorious for risks like thermal runaway, where heat spirals out of control, leading to fire or even explosion. In an aircraft, that's unthinkable. Aviation-grade batteries must withstand high altitudes, pressure changes, extreme cold, and vibration, all without failure. That's why NASA, the FAO, and companies building electric planes are investing heavily in safety measures. Advanced battery management systems, fire-resistant materials, and strict certification standards are the backbone of making electric flight viable. Then there's thermal management. Batteries naturally generate heat when charging and discharging, but in the confined fuselage of an aircraft, cooling space is limited. Engineers are experimenting with liquid cooling, phase change materials, and innovative pack designs to keep temperatures under control without adding more weight. Placement of the batteries inside the aircraft also matters. They must be positioned carefully to maintain balance, stability, and crash safety. The sustainability question also looms large. Batteries don't just need to work in the air, they must be produced, recycled, and disposed of responsibly. Researchers are exploring recyclable chemistries, greener materials, and ways to reduce life cycle emissions so electric aviation truly delivers on its environmental promise. Looking forward, new frontiers are opening up. Lithium air and lithium CFX chemistries could push energy storage far beyond today's limits. Wright Electric is even exploring molten batteries, high-temperature systems that could pack in more active material and dramatically reduce weight. These concepts face tough engineering challenges, but they highlight the level of innovation racing ahead to power the skies. Charging infrastructure is the final piece of the puzzle. Unlike cars that can plug in almost anywhere, aircraft need dedicated, high-power charging stations at airports. Fast turnaround is essential to keep commercial flights on schedule. Wireless and megawatt-class charging systems are already being explored to make this possible. The big picture: electric aviation won't replace jet fuel overnight. But step by step, regional commuter planes, air taxis, and urban mobility vehicles are proving what's possible. Each advance in battery technology, safety, and charging brings us closer to a day when flying doesn't have to mean burning fossil fuels. The bottom line: batteries are the linchpin. They determine how far, how fast, and how safe electric aircraft can fly. The challenges are enormous, but the progress is undeniable. If innovation continues at today's pace, the dream of boarding a large, all-electric airliner may not just be science fiction, it could be the sustainable future of aviation.